think and write at the same time this stuff, which is definitely my case. I had a hard time really thinking about it deeply and writing at the same time. So you have to figure yourself out. Work on it. All right. So these are some of the essential skills of derivative technique, if you will. It's usually chapter 2 in a textbook. And let's be very clear from the start that there's a huge difference between the how and the why. I would love to actually try this, but I know I've tried this on pre-algebra students. I have taught pre-algebra students how to take the derivative by power rule. And so I could teach in 20 minutes how a pre-algebra student could take a derivative, and I just say, okay, bring this number down, and don't worry about y, it's fine, and you just call this x down, and then you reduce this by 1, and boom, there's the derivative. Now, can they take a derivative? Yes. Do they have any idea what that means? No. No. Okay, so please do focus not just on the very nitty-gritty small point details, and that's just a power rule derivative, that's not hot derivatives, and the really deep concepts of why. All right, so here we go. At its heart, for 5,000 years, people couldn't find instantaneous change because it's kind of ridiculous. How do you find change between one point in time and itself? Can something change between itself and itself in no time? No. Well, certainly not. And likewise, graphically, can you find a single line through a single point? No. Surely not. There are infinitely many. So for 5,000 years, the idea of how do you find instantaneous change? We just can't. You can't find change between the point themselves. And that's because they didn't understand, it didn't have the concept of a limit. They didn't have limits. When they found limit, they found calculus. And so this then is that idea. They were able to say, well, I can estimate the average rate of change. So let's call this A, yeah? And I could estimate the average rate of change by taking a point A and a point a little away. Do you agree that I could change A by 5 units or 4 units? I'll just call it generally delta x units. Now, if I start at A and go delta x over, where does that put me? A plus delta x. I could then find the slope between 2 points, and that is called what? What's the slope between 2 points? Secant slope. And as far as rates of change, that's an estimate. It's an average rate of change. It's an average rate of change over an interval. And it's possible, it's so cool to think of this, but if I were able to find every slope in here and average them, that's what I would get is that average slope. That's the average slope over the whole interval, if it were possible to average all of them. It's the average. Now, surely some of those are less than that, and some of those are more than that. It's the average of them. So the idea then, as you know, is to take those 2 points and get them closer and closer and closer together. The points you use, let's jump down to here, the points you use are A and F at A for the x and y of the original point, and the other point is A plus a little more. You probably used H, didn't you? You used delta x? Okay, H is less writing. Delta x, when you first introduce it, makes more sense to somebody. What is H, you know? But I find if you use H, it's fine. It's less writing. F of A plus delta x, I'll just keep going with it. All right. Now, when I use those 2 points, what's the slope between them? Change in y is F at A plus delta x minus F at A over change in x, which is delta x. By definition, that's what delta x is. I guess you could say A plus delta x minus A. Doesn't that put you at delta x? Now that's the slope, and that's the secant slope or the tangent slope? Secant. That's the secant slope. The only way I get a tangent slope is if I take the 2 points closer and closer together, so close that the dot looks like one and the same. Well, how do I get 2 points closer together? The limit. What do I take the limit of? Delta x goes to 0. I want to take the gap between the points down to nothing. All right. What is that finding? When I do that calculation, what did I find? The tangent slope at a singular point. The tangent slope at x equal a. So if I did all those how do you say that? Machination? Whatever. All those steps. Would I get a number or a function? At a specific point, is that a actual numerical slope, or is it lots of different slopes? It's one slope. Now that's assuming I use 2 for a, and once I put in a, right? So when you do, this is the derivative at a specific point. It should be a numerical answer. If I wanted then to find the slope at any old point, x, and I used it a little bit away, then that would look more like, let's just go straight down here. The slope between those 2 points would be f of x plus delta x minus f of x over delta x, but I still take the gap or the difference down to 0, right? Now in terms of what I did there, that's not a numerical slope at a specific point. That's more like a rule that gives slope at any x. So it would be a function of x, which is why we call it a prime of x. It's a function of the original, but with a little change. All right, are we down? That's the first definition of the derivative. There are other ideas, but there are other definitions, but they all have the same 2 ideas at the core. Find the slope between 2 points, take the points close together. Find the slope between 2 points, take the points close together. It's always the same 2 ideas at its heart. So in alternate, it's a little different notation. Instead, they call this point A, and rather than use a delta x there, they just said, let this be some other point x that could change. A is a constant. X is any old point on the curve. Therefore, the points would be A and f at A, and x and f at that point. And the slope would be something like f at x minus f at a over x minus a. That accomplishes the slope between 2 points. But again, the whole idea of a derivative is the slope at a point. And we do that by getting the points close together. Which point do we move? X or a? X. A doesn't move. It's constant. It's set. So x needs to move towards a. So what's the limit? X goes to a of the difference quotient or the secant slope. And what am I finding there? Slope at any point or slope at a specific a? Slope at a specific a. Or instantaneous rate of change. All right. So that's usually numerical. All right. Last but not least is symmetric. Say you wanted a slope specifically at some x. Rather than use that point and another point, we're going to use 2 other points on either side. So imagine if I went a delta x above. That would put me at x plus delta x. And then I went at delta x below, which would put me at x minus delta x. Then I found the slope between those 2 values. The points I'm using are x minus delta x and f at that point, and x plus delta x and f at x plus delta x. Those are the 2 points I'm using. And I'm actually not even using the point of interest, x. I'm on either side of it. But I am going to kind of sandwich it in, squeeze it in. I'm going to gradually get the delta x closer to 0, so I get closer and closer and closer, and I'm good. Well, how do I'm going to bypass the slope. Actually, let's just go down to the end. What's the slope or difference quotient? F at x plus delta x minus f of x minus delta x over, what's the delta x, or the change in x between those two? 2x. 2x or 2 delta x? 2 delta x, yeah? Because it's delta x on either side of the middle. And how do I get the points close together? That's the secant slope. Now make it the tangent slope. The limit as delta x goes to 0. It's more like the first definition, and that the gap is taken back to 0. That's called the symmetric definition for good reason. It's approaching from both sides. And it could be used to find, if I had a plus delta and a minus delta, it would be a slope at a point. But in this case that I did, it's the slope at a point. Could be used for x equal a also. It's possible you see a symmetric with a specific point. The Inspire is perfected now, but the 84 long ago had an issue. It was programmed to use the symmetric definition of the derivative. And it, like any calculator, is, as Ms. Cannon says, just a darn good estimator. It doesn't know outcomes. And so when you try to find the derivative of this function, this is a classic investigation, when you try to find the derivative of this function at 0, well, we know that there is no point at 0, so you can't have a tangent slope at a point that doesn't exist. So a good calculus student would say the derivative at 0 is undefined because the function's not continuous there, right? And yet the 84 was programmed to do the symmetric definition and leave off within a 10,000th on either side. What answer did it give when you put that into the 84? Approach it. 0 what? Yeah, if you connected 2 points really close and then said, what's the slope? That's what it was programmed to do. It said, get within 1,000th on either side and calculate. Well, it would say 0, and that's using the symmetric definition. Now, it uses a newer definition now, so it would know it has a problem. But it's just interesting to think symmetric does make a difference. They do make a difference too. Let's go to this guy. Nope, is there something beneath that? Isn't there something beneath that about? Could you do this absolute yes and don't bother? Okay. So, thank you, yes. Here's the deal. Back when you learned Calc 1, or you were starting to learn Calc 1, you actually used the definition of the derivative to find the derivative. So, if you, for example, said, hey, what's the derivative? What's the first function I gave you? Y equals what? X? Square root x. Okay. So, could you do does it say which definition you use? First. How would that start? Let's use h. Limit as h goes to 0 of minus the square root of x over h. Now, surely that's an undefined limit, that's 0 over 0, and you have been taught with limits how to get around that. For example, what would you do? Algebraic manipulation here. You factor by the conjugate, and eventually it would wash out. Now, that's great, but if you recall, you never did transcendental functions, which is to say non-algebraic functions. It's a great problem, one I will probably give you, but what's the derivative of sine? Prove it. So will you. You will prove it, okay? You will have to prove that soon, and it goes to a lot more than just algebra manipulations. Those aren't algebra terms. And so we're going to do that. I think it's a good time to put that in as in when we hit limit rules in set 71 or something like that. So we'll do stuff like that. And it's pretty cool if you're a thinker. It's good thinking exercise. My point, though, is this. If you look at any of those and if you don't think you could do those by hand without the shortcuts, by doing the algebra, then you should practice them. But if you feel good about those, then I'm fine if you just say I'm good. Are any of those looking funky and you want to walk through them together? I can't remember if there's any challenging ones. A really good one is to prove the power laws. I didn't get it to you. Yeah. All right. So if you feel like you want to go over those, fine. Otherwise, let's move on. Okay. So it's more common on the AP test and on tests past the first calculus test in college that you more often identify a limit as a derivative and then do the derivative with the shortcut. So, for example, given the derivatives below, tell which definition is used, what the function is, and at what point. It doesn't say what the derivative is. So, which definition is being used here? Alternative. It's the alternative. It's x approaching a number rather than a delta x approaching nothing. And what is the function? Absolute value of x. And what are they asking you to find? F prime at any old x or at a specific number? That's what I am wanting to see that you can do. Can you identify which of the definitions, what's the function, and at a point or generally speaking? Try that for the rest, please. Feel free to talk it over with your math amigos. I'm trying to learn your notes, your wishes, your names, right? You're welcome. We'll make that fundraise distinct and cold. Ella. So your thing? So if you guys ever kiss me, stuff to your hair and use it, that was it. All right. How are you doing? Where are you at? Maybe none. Need a little more time. Thanks for that feedback. Thank you. All right, take another minute. And let's go, shall we? Keegan, for B, which definition did you say? Alternate. Dan, what function? Oh, that's okay, no worries. Ken, what'd you say for the function? Okay, and what are you finding, Show? F prime at 3. You are finding a derivative at a certain point 3. All right. How about Cole for C? Which definition? The normal one, or the first definition, whichever you prefer. The definition, you can even call it. The normal one's fine. What's the function? Sergio, what's the function? Perfect. And what are you finding when you use the first definition here, Skylar? Is it the definition, is it the derivative at all x's or a certain number? What will this yield? A derivative that's a rule at any x or a certain number, numerical derivative? It's at any x, yes. Okay, you really have two different derivative cases. You're finding a specific derivative slope at a certain point or a general rule that can be used for any x. D. Ben, what definition?
Symmetric.
I agree. What's the function, Lauren? Did you say x cubed plus 3? Yeah. Okay, sorry, I was writing when you were speaking. 3 or 3x?
Oh, 3x.
Okay, I agree. And where did I leave off? Jade, does that is this going to find a derivative at any x or a specific number?
Any x?
Yeah, this is a general derivative here. Okay. Ada, what derivative definition is being used here? First definition. I agree. What's the function, Kylie?
X cubed plus 3x.
Yeah. And what are you finding when you find this, Lindsay? Is it f prime at any x or f prime at a number? F prime at 4, I agree. So that should yield a numerical answer, not a function answer. This one is the one, these start to get funky when they do simplifying. That's hard. Bethany, what definition does it feel like? I agree, you are correct. It is the first definition. A little harder is what's the function, but not a lot harder. Katai, what's the function? So this is a matter of interpretation, but I feel like it's just x cubed plus 3x, and there are possible other answers, but fine. What are you finding, Cindy? F at 4, F prime. F prime 4. Thank you. And G, so that 76 is a little misleading, but I imagine it's the exact same as that. This is really the exact same thing. I just simplified the inside over there. No big deal. G. Lucas, what definition? First. You could say it's the first. It sounds just like that, right? That wasn't my intention. I guess you could say it's the first with it instead of h using x, yeah? Could it also be an alternate? I'm going to go with alternate. Although you're right, you could argue the first definition. What's the function? So this is where it gets funky. If it's alternate, then this is where it really helps to know the definition. Isn't the definition f of x minus f of a? So what's the function? All of that. 4 plus x cubed plus 3 times 4 plus x. That's a bit of a gotcha. And does the alternate find the derivative at a point or generally speaking? At a point. And what is the derivative at this point? As x goes to 0, this would approach, so it must be at the point x equals Good, so that's that time. That's a tricky one. Okay. Is this the right next thing on your notes? Okay. You should be able to estimate an instantaneous rate of change with an average rate of change. Think table. If you had a table of 0, 1, 2, 3, and the f values were -3, 0, 3, 8. If I asked you to estimate f prime at 2, I can imagine, and they would take 3 different answers. What's one way to estimate the instantaneous rate of change at 2? F at 3 minus f at 1 over, what idea are you using there? You're using this metric here. What else could you do? F at 2 minus f at 1 over 2 minus 1. What else could you do? F at 3 minus f at 2 over 3 minus 2. All of those achieve the idea of as close as you can get for one of the definitions. Would you be able to use 3 and 0? What part of the definition of the derivative is that violate? And there's 2 pieces. There's the slope component and the limit component. By choosing 3 and 0, which component are you not using? The limit. You're not getting as close as you can. So they would never take 3 and 0 as the points used. I tell you though, this would be a 1-point part A of a free response, and the point that's lost is between the two. If you say equal, you are out. That is not true. It is not the instantaneous rate of change. It is an estimate. Okay? And so you must be very clear that this is an estimate. It's really the slope between 2 points as a stand-in for the slope at a point. It's an estimate. Be fluent with all derivative notations and variable descriptions. F prime is Newton's notation. Who are the 2 discoverers of the calculus? Leibniz and Newton. Right? Now, Newton used function notation. He actually used a little dot here. And he didn't call it a derivative. He called it a fluxion, which I think is cool. I wish we could find fluxions right now, but he called that a fluxion. At any rate, I don't know where that went, but it was slightly changed, and so we use that notation. Or Leibniz notation is typically something like this. The book, once in a while, Saxon sometimes will throw that in there. I never have seen that in Cal 1 and Cal 2. It's a higher level idea. He's trying to get, don't do that. That's and so when you talk, it's just don't do it. I prefer one of those 2 notations. Do please pay attention to the variable at hand or the function name at hand. On the AP test, and just generally speaking, if it says g of x is blah, 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 but then in all your work you have f of x, well, that's bad. It's just like if I called you Jimmy, all right? I don't use somebody else's name to call you. Use the name they give you. You don't get to call it, I'm going to call everybody else. No, that's not okay. Use the function name they give you. If it's f, call it f. If it's g, call it g. Verbal description. Give me one way to describe or another way to think of the derivative. Give me a way to think of the derivative. Slope of what? Not a point. Tangent slope. Tangent. Equation slope of the tangent. What else? Think rates of change. Instantaneous rate of change. You could also often hear it referred to as the limit of the difference quotient. Now that definitely is a reference to the actual definition of the derivative. But all those could be asked. If I say, hey, find the limit of the difference quotient for the function square root of x, you're not going to come up to me and say, what do you mean? I'm going to say, you should pay attention. You need to know that means the derivative. Okay? All right. Differentiability. There are reasons a derivative doesn't exist. What are 3 reasons a derivative wouldn't exist at a point? Did you learn this last year? Yes? Okay. Jimmy, do you remember some reasons the derivative doesn't exist? Cusp? Okay, so I'm going to call it sharp turn. Could be a cusp or a corner. Cusp is usually used for curves. Corner is usually used for lines. If you have a corner, a line, and a curve, I don't know what to call it. Honestly. What else? Discontinuity. That's at all discontinuities. It could be a vertical asymptote. It could be a hole. Any discontinuity, no derivative. You can't have a derivative at a point that doesn't exist. Yeah. What else? There's one more. Vertical. Yeah, vertical. Now, this is one where you need to be careful because sometimes what people will say, vertical asymptote. Why is that not true or not necessary? I got it already. That's discontinuity. You don't mean vertical asymptote. You mean vertical tangent. Why doesn't the derivative exist then? Think a vertical line. What's the rise or the run? Yeah, that's constant. So that doesn't exist. Okay. Sharp turn is by far the hardest one to prove. I don't know if you had to prove lack of differentiability, but I am going to expect you to prove it. Differentiability implies continuity. Draw a Venn diagram over here. Continuity could be lots of functions. Differentiability is more specific. So if it's differentiable, then it's continuous. Certainly that's true. But the converse is not true necessarily. If it's continuous, it's not necessarily differentiable. Do you remember your converse, inverse, contrapositive? What do you do in a converse? You switch. I think of switching your cons on your feet. You remember that. Switch them. What's inverse? Negate and negate. And contrapositive? Negate and switch. Contrapositive has equal truth. Okay, this are all good things for when you take logic. All right, sharp corners can be shown to violate the very definition of the derivative because the slopes from the left and right are not equal. Use the first definition of x at x equals 0 or the alternate definition of the derivative to prove that f of x is not differentiable at x equals 0. I recommend the alternate definition. This is the best. So I want to find the derivative of this function. By definition, alternate definition, what is it? X goes to a, and in this case, a is 0 of f of x minus f at a, which in this case is f at x is absolute value of x minus f at a is absolute value of 0 over x minus a or x minus 0. Cleaned up, this is the same as the limit as x goes to 0 of the absolute value of x over x. Have you seen that a million times? You do it pops up a lot. That's actually a pretty significant thing. When I go to do the derivative of absolute value functions, you'll see this. We'll talk about that more later. But it's a bit of a pickle because you get 0 over 0 and you can't do algebra. So how do you approach that? What's the method to finding this limit? Say what? Yep, absolutely. So you have to go one-sided limits. When you go from the left, negative 1 over, absolute value of negative 1 over negative 1, the numbers are the same, but the sign in the top is made positive and the bottom is negative. So how do these come out? Negative 1. If you approach from the top, you're talking positives, and does absolute value do anything to positives? So in those cases, the x's are the same, and this comes out to be 1. Well, if the slopes from the left, remember, this isn't just a limit problem, this means slopes. If the slopes between 0 and a point on the left approach negative, and the slopes from 0 and the right approach positive 1, well, if these aren't the same, if negative 1 is not equal to 1, the one-sided limit's not equal, therefore the limit does not exist, and therefore I conclude that f prime at 0 does not exist. Think graphically. Isn't the absolute value graph something like this? And the whole idea of alternate definition is using 0 and some other point. And when I connect these and get closer and closer and closer, what are the slopes always on the left? -1. If I use a point on the right and connect to 0 and get closer and closer and closer, what are those slopes? Well, that's why it's sharp turn. It's not because some math person said, well, I don't like sharp turn. Let's say that. There's a math reason for everything. In this case, it's when you have a sharp turn, you have an abrupt change from one slope to the other with not everything in between. The limit doesn't exist. It must be, write this down, must be locally linear. If I zoom in on this, it needs to eventually start to smooth out across the screen. And no matter how much you zoom in, it's never smooth out. All right, you with me? Do you remember your transcendental derivatives? What's the derivative of natural log? 1 over x, derivative of e to the x. Derivative of the sine of x. Derivative of cosine. Negative sine. Derivative of tangent. So the rest is secant squared. Derivative of cotangent. Negative cosecant squared. Derivative of cosecant. Negative cosecant cotangent. Derivative of secant. Secant. Okay? All right. What's the derivative of constant? 0. What's the derivative if you have a coefficient times a function? What's the process when you have a coefficient? Coefficient stays out front, and you just take the derivative on the function itself, right? What's the power rule? Derivative of x to a power. Bring the power down, reduce it by 1. Clear shortcut in all mathematics. What's the derivative of a sum? The derivative of a sum is the sum of the derivatives. What about the derivative of a product? Is it the product of the derivatives? No, product is the product. First d second, so f g prime plus second d first g f prime. Right? What's the quotient rule? Low d high f g prime plus or minus? Minus high d low f. Did I do that right? I did that wrong. Low d high is g f prime, is it not? Sorry, low d high minus high f d low g prime over low or over the square root of what's left. And the chain rule, when is it used? Chain rule is used when you have a function within a function, a composite function. And what's the rule for chain rule? F prime, you take the derivative of the outside, and what do you do with the inside? Leave it the same, and then you take the derivative of the inside. All right, you also need to be able to use combinations of rules above. So for example, if I said y is e to the sine of x times 3x squared, what two rules would I need to find the derivative? Product rule and chain rule, because you have a function within a function. Shall we walk through that, or you good? Yes. Yes, walk through it. All right. So what's first, the chain rule part or the product rule? Chain rule. It's a product within the chain. So chain rule. The derivative of the outside is the derivative. The outside is the derivative of e, and the derivative of e is the same with the inside the same. That's the chain rule part of it, the first part of the chain rule. Then we multiply by the derivative of the inside, and that's when we need the product rule. So the derivative of the product is the first stays the same. Derivative of the second is 6x plus second stays the same, and the derivative of the first is cosine. And so combinations of rules. And I think that was kind of in the middle of the year, so you should probably be pretty settled with those, but maybe not. And then, this might be a little bit of an overreach, but do you remember kind of implicit differentiation?
Yes.
Okay. So first of all, do you agree that you're differentiating this with respect to x? And you use the chain rule here. So for example, when you do the derivative of 2x squared, the derivative of the outside is 4x, and the derivative of the inside is the derivative of x with respect to x, which is just 1. Okay. But when you go to this guy, it's the derivative of the outside, and there's a chain rule. So there's a product rule, first of all. That -3, do you want to leave it out front or lump it in with the x? What? Leave it out. So -3 out front and inside. So now product rule. First stays the same. That's x. What's the derivative of the second? What's the derivative of y with respect to x? Y dx. Plus second stays the same. Y times the derivative of the first. What's the derivative of x with respect to x? Okay, what's the derivative of y squared? 2y dxu, remember? And the derivative of a constant is always 0. Then what do you do? Solve for dy. Okay. If we need to finish it, we should be good. Did I get it? We're good? Okay. How about last night's homework? How'd it go? Did I post the key?
Yeah, it's like an
Oh, okay. So I'll tell you what, if you're, as long as you did everything you go, you're good. But you're right, you didn't have the answers to the last few. If you're really confused, come in 7th after school. But as long as you gave it a go, okay? Understood? Great. Have a great day, people. Yes, ma'am. Oh, well, you're lucky I have not graded it yet.